So we looked at this partition relation last time. A partition of a set A is cutting up of A into disjoint subsets, so that A is the disjoint union of A1 to AN. Define a relation twiddle on A by X is related to Y, or X twiddle Y, when X and Y are in the same, and these things are known as blocks of the partition. So certainly any X in A is in the same block with itself. So X is related to X. And then assuming X is related to Y, that means X and Y are in the same block, which also means Y is related to X, because, sets have no particular order to the elements. And then transitivity, assuming that X is related to Y and Y is related to Z. This means that X and Y are in the same block, AI, and Y and Z are in the same block, AJ. But Y is in both of these pairs. And Y is only in one block, because the blocks are disjoint. So AI and AJ must actually be the same block. Thus, X and Z are in the same block. So for next time, I wanted to have you prove the following relation on the set of integers. And that relationship is that X is related to Y when X minus Y is even. Let us do a more general version of that. As an example, so first the definition. We say that given integers d and n, we say that d divides n when n is equal to d times k for some k. So n is a multiple of d, or n divided by d is still an integer, or whatever. All these things are equivalent. We write this relationship d divides n. Use this vertical line notation here. So another example of an equivalence relation. So even means 2 divides n. So let n be a positive integer. We define a relation on all of z as follows. So we say x is related to y when when n divides y minus x. That is, y minus x is a multiple of n. This is an equivalence relation on z. So let's prove that it's an equivalence relation. First, you have to show that it's reflexive, right? Given x in z, what do we have to show? We have to show that n divides x minus x. Well, x minus x equals 0, and certainly does n divide 0 by definition? It's one of those sort of vacuous statements, I guess. But by definition, does n divide 0? What's the definition of divides? If, all right.
So for the definition and example, n is becoming d for this one.
No. The m is 0 and the d is, oh yeah, this is, sorry, I used the wrong letters. Let's say n divides m when m is equal to nk. We relate this relation as n divides m. I'm sorry, I got my letters all mixed up in there. All right, so n divides m when m is a multiple of n. Right?
Then yes.
Does n divide 0? Is 0 a multiple of n?
Wait.
Is 0 a multiple of n?
Yeah, because you could have k be 0 as well.
Sure. It most certainly is a multiple of n. 0 is a multiple of every integer, in fact. It's the only one that has that property, but it is. All right, so x is related to x. Symmetry. What was the symmetric relation?
That if x implies y, then y implies x.
Not imply.
Sorry, if x is related to y, that implies y is related to x.
Right. If x is related to y, it implies y is related to x. All right. So what is the first sentence of a proof of this supposed to be? So to prove P implies Y, or P implies Q, assume P is true, show Q is true. Or assume Q is false, show P is false. Or assume P is true and Q is false, find a contradiction. So what should be the first sentence of a proof of X related to Y implies Y is related to X?
If the direct proof would be the nicest one for this, I would say assume P, show Q. So assume X is related to Y is true, and show that that implies Y related to X is true.
Okay, so assume that X is related to Y. This means what? Assume X is related to Y, that is?
That is n divides X minus Y?
Y minus X.
Sorry, Y minus X?
Yeah.
Did you switch it from the original question?
Sorry? What?
Just keep going.
Sorry, what's that?
I was asking if you switched X and Y around from the original question you asked us the other day.
I don't think so. This
originally
is
was if X is related to Y, then X minus Y is even.
Oh, okay. It's actually the same, but I want to do it Y minus X in this case.
Okay.
Yeah, but it doesn't matter. Either or will work. So assume that x is related to y. That is, and then you flip them around. N divides y minus x. That is, y minus x is equal to n times k. All right. Now I have to show that y is related to x. To show y is related to x, I need what? Right. X related to y means that y minus x is equal to n times k. To get that y is related to x, I need what? Y is related to x means what?
That y minus x is
Nope.
an
Not
integer.
y minus x. X is related to y means that n divides y minus x.
Oh, sorry. Yeah.
Well, I'm sorry. Let's just turn it around. I guess this is confusing everybody. N divides x minus y. So x related to y when n divides x minus y. I apologize. Let's just do it. It's more customary to do it the other way because of a certain reason, but we'll not worry about that reason. So assume that x is related to y. That is, x minus y is a multiple of k. So now I want to show that y is related to x, which means what?
Does it flip it?
Yeah, which means that y minus x, is a multiple of n. This is not part of the proof. I'm just working something out here. So if x minus y is equal to n times k, y minus x is equal to
Negative n.
n times minus k. All right, it's just the negative of x minus y. When you turn around a subtraction, it just negates it. All right, so it's the multiple of n by negative k. All right, therefore y minus x is n times k. So y is related to x. Okay, transitive. So what is the transitive relation? The transitive relation is that x is related to y and y is related to z implies x is related to z. So we're trying to show P and R implies Q. So P and R implies Q. So 3 ways to do it: direct proof, contrapositive, contradiction. So let's do a direct proof. It's easiest in this case. What's the first sentence in a direct proof here of this property?
Assume x implies y and y implies x. Assume x is related to y and y is related to z.
Yeah, assume x is related to y and y is related to x. Right, that is, or y is related to z, sorry. That is, right, n divides x minus y, and n divides y minus z. That is, right, x minus y is equal to n times k, and y minus z is equal to what? Can't say n times k. We already used k here.
N times c.
N times t. Right, now what do we want? We want to show that x is related to z. This is what we want. We want that x is related to z. Right, that is x minus z is a multiple of n. Right, what could we do to get that x minus z is a multiple of n?
Could you add the left side of the equation together and the right side of the equation together?
Sure, add the equations together. Right, so adding these, all right, what do we get? We get that x minus z is equal to
N, and then parentheses k plus d.
yeah, which is a multiple of n. So adding these, we get this. So what's the conclusion?
That it is an equivalent relation.
Yeah, well, that x is related to z.
Oh yeah.
Yeah, and then that's it.
I have a question.
Mm-hmm.
It seems like the properties of an equivalent relation would apply to all relations. Could you give an example of like a relation that isn't transitive?
Well, symmetry is one that you know. I mean, when you have like this relationship, y less than or equal to x, right? Y less than or equal to x definitely does not imply x is less than or equal to y, unless x and y are equal, right? So this kind of relationship is not symmetric.
I'm more particularly asking about the transitive property.
Transitivity. Well, I mean, you just here's a relation. So a is x, y, z, and r is equal to. You just define it to not be transitive. There it is. So x is related to y is related to z, but x is not related to z. It's not symmetric because x is related to y, but y is not related to x. So, I mean, whether there are any, I mean, this is not like the most natural relation, you know, to think of. It's just some randomly made up thing. You know, which relations are not naturally transitive. Well, that's another story. All right, let's think of another one. Oh, this relationship is called equivalence modulo n, by the way.
What did you say it was called?
Equivalence equivalence modulo n. So, like for modular, it's the basis of modular arithmetic. If you're familiar with that already, which all of you are, although you may not know it. So here's one dealing with even and odd rather than these multiple kinds of things. Consider a finite set A. Okay, and define a relationship or a relation on P of A. What was P of A?
The power set of A.
The power set of A, which is the set of all x, such that x is a subset of A. By x is related to y when x symmetric difference y, the order of that set is even. Right, so the symmetric difference of two sets. So these two subsets are going to be related when the symmetric difference between them is even. And remember, what's symmetric difference?
It's the union minus. Sorry, it's the
x union y minus.
The other one's name is slipping my mind for some reason.
Intersection.
Intersection, yeah. The N shape.
Yeah. X union y minus x intersection y. Another way to think of it was what? Minus
every element in x and y, in x or y that isn't an x and y.
Yeah. Right. X minus y union y minus x. Well, what I would like to do is to prove this is an equivalence relation without actually just showing those three properties. Well, no, actually, I think we have to. Look, it's fine. Let's do it. Hold on. Yeah, so before we start on this, let's go back to, let's just talk about a certain fact. So let's use this fact. All right, the sum and difference of even numbers is even. Just the sum of several even numbers is still even. Right, it has to do with that previous example when you talk about equivalence modulo 2. If you want to add two even numbers, well, it's not immediate from there. But, I mean, let's not belabor this point. We'll just assume that it's true that the sum of a bunch of even numbers is still just even. Okay, so how about the reflexive property? Well, x, symmetric difference x is going to be what?
Nothing.
Is the empty set.
Oh.
Yeah,
Zero is
nothing,
even?
the empty set. And so the order of x, symmetric difference x, is what? Even or odd?
Even.
Yeah. Is 0, which is even. So x is related to x. Symmetric. So assuming that x is related to y, we have that x symmetric difference y is even. Right? Thus, x union y minus x intersect y is even. But intersection and union are defined with what logic operation?
And or respectively.
They're defined with and or, with the similar symbol. And or are what? What tautology applies to those? That would be useful in this instance.
Commutativity.
They're commutative. So by commutativity, right, y union x minus y intersection x is equal to this x union y, right, is even as well. Right, which is, I guess I should put the symmetric difference symbol. Right, so what? Y symmetric difference x was even too, which means
It's symmetric.
sorry.
Well, x symmetric difference y is also even.
Well, we assume that's true. That x symmetric difference y is even. This one means y symmetric x is even, which means what as far as the relation goes?
It's symmetric.
Right, but what does this mean as far as the twiddle goes? This means this is even.
Oh, it means y is related to x.
Y is related to x. Assuming that x is related to y, we have that y is related to x. Transitivity. Right, so assume that. What? For transitivity, what do we assume?
X related to Y and Y related to Z implies, well, that's what we assume.
You assume
try to
X is
find
related
that.
to Y and Y is related to Z. Yeah. So assume that X is related to Y and Y is related to Z. Right, that is X symmetric difference Y and Y symmetric difference Z is even. Let's look at the Venn diagram of three sets. So we're talking about three sets here. All right, we have X, Y, and Z. So the sets X symmetric difference Y and Y symmetric difference Z consist of the following cells of the Venn diagrams shown. Well, let's do all three. Whoops. And X symmetric difference Z consist of the following cells of the Venn diagram for X, Y, and Z. Right, so X symmetric difference Y, Y symmetric difference Z, and then X symmetric difference Z. So what about X symmetric difference Y? Which cells in this Venn diagram correspond to that? Right, where X symmetric difference Y, just when you have two sets, right, is this area and this area.
It consists of every cell except X and Y and X, Y, and Z.
And the Z without the X and Y. So, it's this cell, this cell, this cell, and that cell. All right, X X symmetric difference Y are these cells here in the Venn diagram for 2 sets. So within the Venn diagram for 3 sets, they're right there. Okay, and let's give some numbers here. All right, so we'll say that this is A1, A2, A3, A4, just for the number of elements in each cell. Here, Y symmetric difference Z is this cell, this cell, this cell, and this cell. And we'll call these B1, B2. Oh, well, this one is already, well, maybe these, let's do it this way. Didn't work out as well as I thought it would. All right, so we'll call this A, B, C, D. So this one is A. That's the only one shared in D. A, D, and then we'll call these E and F, like that. And then X symmetric difference Z would consist of this cell, this cell, this cell, and this cell. And this cell has E elements in it. This cell has C elements in it. This cell has B elements in it. And this one has F. All right, say that the number of elements in each of those cells is as indicated above. So the lowercase letters in each cell indicate the number of elements. In each cell. All right, since X symmetric difference Y is even, therefore, the order of X symmetric difference Y, which is equal to what in terms of A through F? In terms of A through F, X symmetric difference Y is equal to what?
A plus B plus C plus D.
A plus B plus C plus D is even. And then Y symmetric difference Z, which is equal to A plus D plus E plus F, A plus D plus E plus F is even. Now, we're looking for B plus C plus E plus F to be even as well. Right? We've got A plus B plus C plus D is even. A plus D plus E plus F is even. We would like B plus C plus E plus F to be even. How is that going to happen? X symmetric difference Z, which is equal to B plus C plus E plus F, which is equal to what? So we would like that to be even. And remember, the sum of even numbers is even.
The only way for the first two to be even would be for all of the elements to be even or all of the elements to be odd.
Could be one even or two even, two odd. Also, there's a more direct way of doing this. Remember, when you multiply something by 2, whether it's even or odd, it becomes even. Sorry. When you multiply a number by 2, you get an even number, whether the original number was even or odd. It doesn't become even, it stays, yeah, you know what I'm trying to say. When you double something, you get an even number. What happens when I add these two guys together? What do I get? Do I get this?
No, but you do get that plus additional even numbers.
Yeah, you get that plus additional even numbers. So what do you get? You get B plus C plus D plus F. Right? How can I add in even numbers there? Right? Plus 2A minus 2A. Well, plus 0 plus 0. Plus 0 plus 0, let's just do it that way, which is equal to B plus C plus E plus F plus 2A minus 2A plus, what's the other one that's missing? D. Plus 2D minus 2D, which is equal to B, right, which is equal to A plus B plus C plus D. So I put this A with that, and then and this D with that. So I put one A and one D with B and C. And then one A and one D with E and F. And then I still have the minus 2A minus 2D. Right? I just added 0. It stays the same, right? And then the 0 I write as 2A minus 2A and 2D minus 2D. So I take B and C, I add an A and add a D, group them together. I take the E and F, add an A and add a D, and I still got my minus 2A minus 2D. But this is what? A plus B plus C plus D.
Even?
Yeah, it's X symmetric difference Y. Well, yeah, so all of them, right? Which is even. Right, this is even. Right here. This is even. Right here. And then 2A and 2D are
Even because
both even. Yeah, these are all even. So this is just a sum of even numbers, which is a sum of even numbers. And so is even. This is even. X symmetric difference Z. Therefore what? What's
X is related to Z.
X is related to Z as required. So that one actually took a little bit of doing, but we got it done, right? So we assumed that was a whole page and a bit. Assume that X is related to Y and Y is related to Z. That is, X symmetric difference Y as even order and Y symmetric difference Z as even order. Looking at the Venn diagram for 3 sets, X symmetric difference Y is the red, of the 7 cells shown for the Venn diagram for 3 sets. X symmetric difference Y consists of these 4 cells. Y symmetric difference Z consists of these 4 cells, and X symmetric difference Z consists of these 4 cells. So say there's A elements here, B, C, and D elements there, A, E, D, and F elements here, and therefore, E, C, B, and F elements there. Well, we already know that X symmetric difference Y is even, and that's A plus B plus C plus D. We already know that Y symmetric Z, the order is even, and that's A plus D plus E plus F. And we would like that this is even. B plus C plus E plus F. And there it is. Well, B plus C plus E plus F is B plus, whoops. I changed some letters. What happened here? B plus C plus E plus F is B plus C plus E plus F plus 0 plus 0, which is B plus C plus E plus F plus 2A minus 2A, 2D minus 2D. So now I got A, B, C, D, A, D, E, F, minus 2A minus D. Those are all even. Sum of even numbers is even. So that is X symmetric difference Z being of even order. So X is related to Z. So that's an equivalence relation on the power set of a finite set. Of course, you can't use infinite sets because then no such thing as even and odd anymore. All right. So more on equivalence sets next time. Equivalence relations. If you remember that partitioning relation is an equivalence relation, and what we're going to show next time is that, well, actually all equivalence relations are partition relations. So all these equivalence relations that we just did, all they do is partition your set into, they partition your set into disjoint subsets. Those disjoint subsets are called equivalence classes. It's pretty cool. All right, so homework due by 5, and other than that, we'll see you on Friday, okay? All right, guys, have a good day.
Friday, have a good one.